Hi everybody, welcome back to the channel. And so today we're going to talk about this particular paper that's appeared on the archive. It appeared 1 week ago, and it's from the group mainly in Singapore, and they're claiming entanglement between a superconducting qubit and a tardigrade. If you're not familiar with what a tardigrade is, it's also known as a water bear. They're tiny creatures that are water dwelling. They're about 0.1 millimeters typically. And one of its features is that it's extremely resilient under extreme conditions. So people have been looking at these creatures for some time because they can survive, say, in space, in extreme vacuums, or you can boil them and they still survive. You can freeze them, they're still fine. And so they're thought to be one of the most resilient types of creatures. What happens when you freeze them is that they enter this dormant state that you can keep them like this for maybe like 20 months and then revive them, come back to life. It's interesting in the context of this superconducting qubit because, as you might know, superconducting qubits, you got to cool them down to very low temperatures. So typically they operate around 10 millikelvin or below. And so if you stick one of these inside a dilution refrigerator, then they enter this dormant kind of state, right? So what they did here is to stick a tardigrade on the surface of a superconducting qubit chip, and what they're claiming is that they've observed entanglement. What's interesting particularly about this is that they performed the entanglement experiment, and then they actually could revive the tardigrade back to life. The tardigrade was returned to its active form after 420 hours at the sub 10 millikelvin temperatures and 10 to the minus 6 millibars, which is actually a kind of a new record in itself for these kind of extreme conditions that the tardigrade survive under. So this obviously has connotations of the Schrodinger's cat thought experiment. So, of course, in Schrodinger's cat, you have a cat that's either dead or alive, and it's actually entangled with a state of an atom which might decay or not decay. And so in this case, it's not that the tardigrade is alive or dead, it's that it's in supposedly one of two states, and it becomes entangled with the state of a qubit. So it sounds very similar to this Schrodinger's cat experiment. So when this first appeared, people went a little bit nuts on the internet over it, and so it was claimed to be the first multicellular organism to be quantum entangled. But then more recently, people have been starting to dispute this claim that actually entanglement was observed. And there was quite a lot of discussion on Twitter about whether really these results stack up. So what we're going to talk about today is what's happening in this paper. I gave a bit of a read of this paper this afternoon, and we'll take you through those results. As I said, basically the setup is like this. You have a tardigrade on the surface of a superconducting qubit chip. So this is actually just a 2-qubit chip. So there's qubit A and qubit B. They're separated by about 1 millimeter. And what they do is they stick the tardigrade on a piece of filter paper. For some reason, it's sort of upside down. The tardigrade's under the filter paper. I don't really understand why. Maybe it's just so that they move it. They can move it around like this. And then they put that on the surface of the qubit. And what they do is they measure the frequency of the two qubits. Of course, qubits have some frequency, the energy separation between the two levels. And these two qubits are in a microwave cavity. So this means that you can actually couple the two qubits. Okay. All right. So the first experiment just goes something like this. They simply measure the frequency of the two qubits. So in this experiment, actually, qubit A is not really touched at all. So it's just sitting there. Qubit B is the one with the tardigrade that's sitting on it. And what they find is that with the tardigrade, the actual frequency of the qubit shifts a little bit, around about 9 megahertz. Basically, what they do here is to model the tardigrade by some material which has some dielectric constant. Okay, so biological materials typically have permittivities in the range of 4 to 30. And so basically what they say is they perform a numerical simulation of some dielectric medium that's sitting on top of the superconducting qubit, and they perform electric field simulations, and then they basically deduce what the qubit frequency should be based on the presence of this new dielectric material that's just sitting there. So they model the tardigrade by a cube, which is of diameter 100 micrometers across. And what they see is that the frequency shift is pretty much consistent with what they observe. So they see a 9 megahertz. And that, if you use a permittivity of 4, then that agrees pretty much. And that's on the lower range of what typical proteins are. So what they do at this point is to model this with a model that looks something like this. So on the left here, we've got the transmon qubit. That's the actual superconducting qubit. The lower two energy levels are the ones that are used as the qubit states. And they model the state of the tardigrade by a bunch of harmonic oscillators. So these might be some electrical charges that are inside the tardigrade. And so what you have on the bottom here is that model. So we've got the qubit, that's the sigma z, and then all the harmonic oscillators are the bosonic terms there. And they suppose that there's some kind of coupling between the harmonic oscillators on the tardigrade and the superconducting qubit. And this has some typical Jaynes-Cummings forms, so this V Hamiltonian that you have here. And basically what they say is that, well, if you have some Hamiltonian like this, this will cause an energy shift of the excited state. It won't cause any energy shift of the lower state, but it will cause an energy shift of the excited state, because basically, like, if you haven't, you've got to remember, this whole thing's cooled down to basically extremely low temperatures, right? So if you have some excitation that's in this one state there, then this excitation can go across into the tardigrade and then, maybe bounce back. And then you have some state, which eventually is this state E that you have here. And so this is like some kind of entangled state where the excitation is either on the qubit or in the tardigrade. And this psi 1 here is a state where there's like one excitation in the tardigrade. And so basically this is like the first part of their results. They say, look, there's an energy shift. We observe an energy shift, and then we have a model, and it can predict that the energy level of the excited state will be shifted. And so, this is like an entangled state. And so, look, it's entangled with the qubit.
I'm not sure I'm convinced the energy shift demonstrates entanglement. I think you would need to perform some tomography on the tardigrade and qubit to know there was an entanglement.
Exactly. Exactly, yes. So, just because you saw an energy shift is not really conclusive that there's entanglement, right? But let's keep going. There's more results. Okay. All right. So the second experiment that they did was something like this. So they bring in the other qubit, right? Remember, the qubit A wasn't really taking part in the first part of the experiment. So because they can couple the two qubits together, they can do a simple circuit like this. They can perform a Hadamard gate on the qubit B in the tardigrade, perform a C0 gate. And then what you should get is this tangled state of qubit A and qubit B, right? But then because qubit B's got the tardigrade there, what they're saying is not just simply that the qubit B is like state 0 and 1, but actually it's like this state G and E, which is this state that we had before, which is this, state that's mixed up with the tardigrade. Okay, so what they do is they perform tomography. And what's important here is they perform tomography, but it's tomography of basically the two qubits here again, right? So this 0 and 0G, 0E, this is like 0, 1 are the states of qubit A, and then E and G, again, states of the qubit B. Again, they're not really measuring the tardigrade exactly. They're just basically assuming it's the collective state of the tardigrade and the qubit, and then saying that they're measuring the that composite system and calling it E and G. Okay, and then they show, okay, well, yes, you get something very similar to this entangled state that is consistent with this circuit, the fidelity of 82%. And then finally, they show some, I believe these are theoretical calculations, right? So if you look at this state E, right, this is some kind of, as I said, entangled state between the qubit and the tardigrade, but in the second part of the experiment, also with qubit A. Okay, so it's if you prepared this state that we had before, Bell state, but mixed with tardigrade, then you would have some tripartite entangled state. Okay, and so if it's tripartite entangled, then you can look at the entanglement between different sections of this. So, for example, you can look at the entanglement between qubit A and then qubit B and the tardigrade. That's the blue line. You can look at the entanglement between the tardigrade and then the other two qubits. Or you can even look at what's called this pi tangle, which is some kind of genuine tripartite entanglement measure. And basically all this shows that there's some entanglement involved. But again, all this is basically assuming that that's the state that you have, right? It's not really direct experimental measurement of it. In fact, I believe it's just a theoretical calculation of the state that you have, and then you just calculate these quantities. So, and then that's it. Are you guys convinced?
For me, it looks like tardigrade acts like a bath.
Yeah.
And they measured some decoherence.
Yes.
So it didn't have to be a tardigrade.
Yeah, you don't have to.
Yeah.
It can be random.
Yes, that was one of the comments. Like basically, a piece of dust would give the same effect.
Yes.
But it would look less cool.
Yes, it would be less cool if it was dust.
Now, I think I'll give some credit. I think it is really cool that they actually push the conditions for which a living organism can actually be revived. I think that's
yeah.
to talk
I mean,
about.
perhaps that's the actual breakthrough, and that's what people are saying. Yeah.
Imagine when they try to revive the tardigrade, they're like, "Oh, come on, man, wake up!"
Yeah.
Come on.
Maybe the end goal is to train a tardigrade to control the qubit.
Well, it is a cool idea because they can survive that. Right?
Yeah,
So
I think
that's
it's
the
the only
nice
reason to take the tardigrade because it can survive under the superconducting conditions.
I wish I was
the
a
low
tardigrade.
temperatures.
Well, yeah, they survive, but are they still the same before and after the That
No.
means the internal, or I don't know whether is it the internal structure, the behavior, or whatever, but are they still the same?
I mean,
Two tardigrades enter a bar, and one of them says, "You have no idea what they just did."
I got entangled with a qubit.
Haven't seen you for like how long? 2 months? Like
420 hours.
haven't seen you.
Booba, you're not convinced. Why are you not convinced?
I don't know.
You don't know. You sound severely disappointed.
Everybody's
Will you be convinced if they repeat exactly the same thing in space?
Still, like, why are they considering qubits A plus B as two? I don't know.
I mean, they didn't really need to have two qubits in here. I mean, you could, if you really had entanglement between B and the tardigrade, then that would be enough, actually.
Yeah, that's a qubit actually. So that's what I'm not really getting at. The extra one is, I don't know, it's confusing.
But instead of measuring the qubit, why don't they measure the tardigrade? What change does it bring to the tardigrade if it's entangled to a qubit or not?
I guess because they can't.
I'm wondering.
Good point.
Well, it's hard. I don't know. I mean, I don't know how to measure a tardigrade either. So,
Well, you want to measure the change of the tardigrade itself under entanglement?
I'm wondering if IBM Eagle processor will start providing tardigrade modules.
Yeah. Well, Jay Gambetta was pretty critical on this on Twitter.
So there won't be like 128 tardigrade processor. by
No.
IBM.
No.
What a shame.
Yeah.
It is a shame because I think tardigrades are pretty cheap. I'm just wondering if it's tardigrade or tardigrade controlling the qubit.
Very deep.
But just imagine, I mean, the tardigrade got revived and now he's forever entangled with this processor.
Yeah.
Yes.
Imagine it's like a CNOT gate and tardigrade is the control qubit. So tardigrade is controlling the processor, basically.
Can we put the tardigrade in the PEC?
Well, yeah, that would be lower temperature. So maybe that would be, I don't know.
Yeah.
You'd have to laser cool the tardigrade, and that's even more. And the pressures would be lower, I guess. All right, so we'll leave it there, and we'll see you for the next video.